different turn today. So let me explain some just very basics about maximum likelihood estimation. This is something that I give to my students in my undergraduate class quite a bit. In statistics, we're really interested in looking at the difference, or I'm sorry, the relationship between samples and populations. And the two different directions create an interesting contrast. For example, this direction, if we start out where we have our parameters that are known, then we can determine the likelihood of getting something from the sample using probability. So, for example, my population is a deck of cards. I have a standard deck of cards, 52 cards. It's ace of spades, diamonds, all this stuff. I can determine the likelihood of getting a particular sample, for example, drawing the ace of spades. I can make this probability, I can calculate this probability because I know the deck of cards that I'm drawing from. Now, if I come in and lay 5 cards down on the table and I don't tell you what they are, and I pick up one at random, and clearly we can't determine the probability of getting, for example, an ace of spades because we don't understand, or we don't have the knowledge of the population from which we're drawing. All right, clearly probability, is an important branch, but in statistics, and more in terms of data analysis, we usually focus on the reverse. In other words, from our sample, we have some measurements that we've observed. And those things are fixed. There's no longer a probability. We have our data. Our data is what it is. And we want to use it to estimate something that's unknown. And usually we recall that our unknown parameter. So let's talk about the difference again between probability versus likelihood. Probability again, we can say that the probability of an event dependent on certain parameters within our model, can be calculated as P of X given some parameter. Likelihood, on the other hand, does the reverse of this. It looks at the likelihood of a particular parameter given our data. Now, here's an example kind of geometrically. Let's say that I'm focusing on a normal distribution with mean mu and a variance. And I collect some observations from the normal distribution. And let's just say, for example, that my observations are 115, 110, and 108. Now I look at different distributions, and I tell you what, for this situation, let's just go ahead and let's just keep it really simple here. And let's just say that our variance is set and our variance is equal to 16. So mu, if you can think about it, could be anything. So how likely does it seem if we have a distribution mean of 100 with this data? Well, this data has an observation of 115, an observation of 110, and an observation of 108. There's a chance that we could get this data from this distribution with a mean equal to 100, but it's probably more likely that this distribution, or I'm sorry, this data came from a distribution with mean 101. It's probably more likely this data came from a mean of distribution, or that has a, I'm sorry, the normal distribution with a mean of 102. And in fact, we can use just a little bit of common sense here. I'm not really sure what the sample mean is. But the sample mean of 115, 110, and 108, it's probably much more believable at least more likely that the mean of our distribution was actually our sample mean. So in other words, that's what we're trying to accomplish here. We're trying to think that our parameter could be anything. So our parameter is unknown. Unlike probability, where our parameter is known, and we're kind of undoing the process that I'm getting ready to teach you here, in that we can use probability to determine to determine the probability of getting a particular measurement from this distribution. We're actually reversing this and saying, well, we've got our data. What parameter over here seems most likely to have created this data? Now, sometimes it's intuitively clear, but as we probably know in mathematics, or at least we should know in mathematics, we need to develop theory and we need to develop proof on this. So, the first thing I want to do is I want to start out with a very, very simple example. So again, before we go on, let's think about probability. What does it do for us? We have a known parameter. And we can use that to predict outcomes. Likelihood. We have data that we have collected. And we can use this to estimate the parameter. Now, first example I want to take a look at is really, really simple one. And let's say, I don't know, what can we do here? Let's keep it real simple. Let's say we toss a coin. N equal 100 times. And let's say we observe I don't know, 45 heads. So obviously we have 55 tails. Unless we have a three-sided coin, this is clearly believable, right? Now, what we want to do here, we would think that P is equal, well, I've moved my deal around here. Well, okay. So we would think that that we're drawing from a distribution of 0.50. So we could look at the likelihood. We could say, I need to go back here and get, we have 45 heads and 55 tails. Okay. Need to keep this in really, really handy. Okay. So we can say that the likelihood, if we are drawing from a distribution where P is equal to 0.50, in other words, the probability of getting a head is 0.5, probability of getting a tail is 0.5. After observing our data, could be found by taking 100, choose 45, 0.5 times 45. Now let's calculate this. And I'm just going to use my my calculator here. So yeah, I'll do it. If you've got a TI-84, TI-83, if you'll go to Math, which is right under your green button. So what I want to do here is I want to go 100. And then times the rest. So, all right, let's go 100. Math, go over to probability and go NCR. So I'm going to choose 45. Multiply by 5 raised to the 45th power. And multiply by, okay, forget I said that. It should be 0.5. So let me do this again. So n choose 45 times 0.5 raised to the 45th power times 0.5 raised to the 55th power. Now you can see what we're doing. We got a binomial situation here because we've repeated something 100 times. Each event is independent and each has equal probability. So according to my calculations, we have a 0.0485 likelihood of, if you will, collecting this data if the parameter is 0.5. Okay, now let's see what else happens. So what we can do over here, let's start a kind of a summary of our. So what I want to do, see, we've got a proposed parameter, and then we're going to look at the likelihood. And we found when we proposed that the parameter is 0.5, we get a 0.0485 likelihood. Well, common sense kicks in a little bit here and said, no, wait a minute, we got 45 heads, and we got 55 tails. So possibly the distribution we're drawing from, maybe the coin's not fair. And clearly we could test this using an appropriate test of hypothesis, but let's calculate the likelihood. Parameter value is 0.48, given our data. So I'm going to do a little bit of the power of the eraser here. You've got this, you know, you guys have this on video. I always hated those professors that kind of wrote with their right hand and, you know, erased with their left, but you've got the luxury of having this on video where you can stop it. So guys, what I want to do here is I want to go again, choose a likelihood. So I've got 100, choose 45. That's maybe the ugliest zero in the history of zeros. And now I want to go 0.48 to the 45th power. 1 minus 0.48, which is 0.52 to the 55th power. So, again, we'll go 100, choose 45, times 0.48 raised to the 45th power. Hate this new operating system on my calculator, in case you cared. All right, so the likelihood here is 0.0668. I'm glad there wasn't another 6 there. So observing our data, it was more likely that our data came from a binomial distribution with parameter 0.48. Well, intuitively, we would think that if we set something higher than 0.52, which is, again, further away, we're going to figure that, you know, most likely we're going to get something that's even going to be less likely. So let's go ahead and calculate that. We're getting pretty good at this game now, right? So we can just use second function entry. So we have our parameter of 0.52 raised to the 45th power, 0.48 raised to the 55th power, and just as we would expect, the likelihood of observing our data with p being 0.52 is much less than it would be here. Now, we're looking for, I want to look on the other side of the 0.48. You guys know what we're going to give, but I want to go ahead and take a look at that anyway. So we know what this stands for now. What do you think is going to happen when we come in at 0.47? Well, the calculation again can be done very, very easily. So we have 100, choose 45, and we want 0.47 as our p, and 0.53 as our 1 minus p. And I get a syntax error, that's cool. And we get No. Guys, I'm telling you something completely wrong. I'm getting my 48s, my 45s. We're expecting, since there was 45 out of 100, what I would like to do, forget the last 3 minutes. It was a complete and utter garbage. What I want to do is, since we have 45 out of 100, observe 45 out of 100 tails, what I am intending to do is set p calculate the likelihood for 0.44, 0.45, and 0.46. So again, let's do this very, very, very quickly. So I'm going to calculate the 0.44 first. Again, you've got on your calculator, you've got the second function entry key, which is super duper cool here. So this is going to be 0.078, and make the same calculation for 0.45. So here we get 0.0. Let's just call it 0.08. And for 0.46, you're going to get the obvious. Well, not the obvious answer, but the obvious is going to be less than the 0.08. So what we might want to say, therefore, is in general, when we have a binomial distribution, that the MLE of our distribution is going to be x over n. Well, you know mathematics intuitively. I think this is a reasonable statement, but boys and girls, we need proof. But anyway, we're just getting this the idea of maximum likelihood estimation going, and this video we're not going to get into the proof of anything. The next two videos, possibly even the next three videos, we will. So guys, binomial is clearly a discrete distribution. But what happens when we have a continuous distribution? Well, yes, probability deals with area under the curve. Now, this is more of an intuitive approach to looking at a maximum likelihood estimator of a continuous distribution. So I don't know. Let's say that we have some observed data Okay, I'll tell you what I'm going to do. I keep resetting the screen, and I don't know how to get it back, so I'm just going to shut things down here. Reset. Hopefully my screen will be back where it should be. Guys, there is clearly a learning curve to this this process, as you can well tell. So let's say that we have some data that comes from a normal distribution with an unknown mean. And guys, we'll assume that possible outcomes for the mean range from negative infinity to positive infinity. And let's say that we have a known variance. And I don't know, let's keep it kind of simple here, and let's just say that the variance is 16, so obviously standard deviation is equal to 4. And here we go again. Guys, I'll give you extra credit if you can tell me how to set this screen back. I can sure mess it up, but I can't fix it. All right, so what we want to do is we want to look at the maximum likelihood estimate of mu based on our data. Now I'm going to give you a very, if you will, intuitive approach here. Okay? Now, let's say that we have collected the following data, and I'm going to keep it really, really, really simple. 100, 105, and 110. Now, possibilities for mu. Well, infinitely many choices for mu. But let's take one just kind of for the heck of it. And let's say that we think, well, you know what? I think this data came from a normal distribution, mean 98. Again, our variance was, what would I say, equal to 4? Yeah. So we look at this. And we're sort of hypothesizing here, if you will, that our data came from distribution mean 98. So we just happen to get a 100, a 105, and a 110. Is that possible? Absolutely, it's possible. Is it likely? It could be. Okay, so what I want to do is I want to think about how likely this is in terms of probability, which would be area under the curve. So if I can think about the area from 100 to 98 and sum up the area from 105 to 98, and then look at the area from 110 to 98, it would make sense that of all the means that I've got that are possible, that the area from my mean to my observation would be the least at the one that was most likely. So guys, your calculator, you have a normal CDF key. And so if I want to find the area from 98 to 100, so again, we're proposing here that we're drawing from a distribution with mean 98, standard deviation 4, and we have the observations (100, 105, and 110). And from a very intuitive approach, we can look at the areas from 100 to 98, 105 to 98, and 110 to 98, and get an indication of the likelihood, if you will, that our data came from that distribution. So again, if you go second function distribution on your calculator, you have a normal CDF key. So normal cumulative density function. We could get into integration here, and we actually will, but it's not the purpose of this video. So if we want to go from look at the area under the curve from 98 to 100, when we have a mean of 98, standard deviation equal to 4, then I could look at the area from 98 to 105. And then I could look at the area from 98 to 110. So the total of the area here is going to be really easy to find. If I can keep from making a typo. All right, so the total area, and obviously this is not a probability, this is total area, is 1.15. Now let's make a proposal of 102. Now guys, again, we have infinitely many choices for mu. And I'm just looking at a few of these just to give you an indication of the way that we may intuitively, not mathematically, intuitively look at which distribution was more likely to our observed data that it came from. So mean 102, and again our standard deviation is equal to 4. We can follow the same as before. So our first observation. Now our first observation, if we have a mean of 102, and now our data of 100, clearly to the left, so we're going to have to use this. Next thing we want to do, same thing. Guys, keep in mind, neither of these examples I've given you have proved anything. I just want to look at things from an intuitive approach. What did we have? 110, was that the next? Yeah. Well, I just made the freshman mistake. Dr. Darbro, why is my probability negative? All right, so we wanted, so we're a mean of 102, so we want 102 up to 110. Again, considering a mean variance of 16. So I'm going to use second function entry key and just go back and change some things. Speaking of probability, what's the probability that I don't make a typo? So then we get a normal CDF of 102 to 110, mean of 102. All right, guys, when I do this, I get a total area, not a probability. Obviously, it couldn't be a probability because our last answer was above 1. 0.94. Now, if we go back to our data, the mean here was Obviously 105. From an intuitive approach, that might seem like a really good guess. For mu, what do you think? If I had $1,000 to bet on this, because I already know the answer, but if I had $1,000 to bet on this and I just had never seen maximum likelihood estimation before, I would think that balancing out my distribution at the sample mean would probably be the best estimate of the parameter. So let's consider that. Let's kind of just say, well, what do things look like when we have the parameter being 105? Now, let's go back and tabulate some stuff here. When we had a mu of 102, we had a cumulative area of 0.94. I think somewhere many moons ago we had a claim of tested 98. We got 1.15. So this is the sum of the areas. So now we're going to test 105. And it's going to be really easy to do again. Second function entry. I'm going to do it really quickly. So we're going to go from 100 to 105. Mean 105. And then we're going to have, well, 105 to 105. That's going to be a pretty easy one. And then we're going to go from what was our other data? 110. So we'll go to 105 to 110 with a mean of 105. And guess what I get here is 0.789. Now I would have kind of, I'll tell you what, let's just go ahead and do that. I was going to tell you kind of as an exercise, take a look at 106, but it's going to be so easy to do, again, since we've got everything set up in our calculator. So let's just make the calculations and look at the cumulative area under the curve between our observations and taking a look at if our parameter is actually 106. So guys, again, it's going to be really, really easy to do in the calculator. So we will run from 100 to 106, mean 106. Then we will go to 105 to 106, mean 106. And then we want to look at 106 to 110 with a mean of 106. Guys, clearly we're going to get something a little bit bigger. 0.87. Now guys, at the end of the day, what have we proved? Nothing. We have proved absolutely nothing. But from an intuitive approach, we might say that our sample mean is the maximum likelihood estimator for mu when we're dealing with the normal distribution mean unknown, and we worked in this case with a known variance, sigma squared. So let's review a little bit. Likelihood versus probability. Guys, likelihood starts with data. Tries to estimate. where it most likely came from. Probability. Starts with a parameter. Okay, hold on just a second. Okay, starts with a parameter and can look at the probability of a particular event. Well, guys, that ends this lecture. Plus, the trash truck is coming. I got to get out and get the trash out. So, until next time.